Hello everyone, and welcome to Lesson 2 of my course on number theory. Today we're going to be talking about modular arithmetic. So first, what do we mean when we say A is congruent to B mod n? All it means is that A equals B plus k times n for some integer k. Or in other words, n divides A minus B. For example, if we see the statement 21 is congruent to 6 mod 5, you can either see that by saying that 21 equals 6 plus 5 times 3, or by saying that 21 minus 6 over 5 equals 15 over 5 equals 3, which is an integer. We often talk about the residue of a number mod a base, and all that means is that when you divide that number by the base, what's the remainder you get? For example, here, if we take a bunch of numbers from 0 through 9, and divide them by 4, these are the residues we get. So we see that if n is 0, then 0 is congruent to 0 mod 4. 1 is congruent to 1 mod 4. And if you continue this pattern out, you'll notice that once you start listing these numbers, the residues mod 4 repeat every 4 numbers. Now that makes sense because if you had a number like this, 5, it has to be equal to, it has to have the same residue mod 4 as 5 minus 4. And 6 has to have the same residue as 6 minus 4, and so on. So your residues mod 4 are just going to be this block of 0, 1, 2, 3 repeated on and on and on. Now let's start looking at some properties of the mods. So the first property that I'll mention is the additive property. If you have one statement like A is congruent to B mod n and C is congruent to D mod n, then we can just add these two and get that A plus C is congruent to B plus D mod n. Here's how we'll prove it. Let's first break these mods into their equivalent statements mentioned above. So A congruent to B mod n is equivalent to A equals B plus k1n, and C is congruent to D mod n is equivalent to C equals D plus k2 times n, where k1 and k2 are some integers. Then we just add these two equations and we get that A plus C equals B plus D plus k1n plus k2n. And note that we can factor this as A plus C equals B plus D plus the quantity k1 plus k2 times n. Now this equation down here is actually equivalent to A plus C is congruent to B plus D mod n, as we've said earlier. Now let's look at another property. If A is congruent to B mod n and C is congruent to D mod n, then A times C is congruent to B times D mod n. To prove this, we'll start by doing the exact same thing we did before. We write A as B plus n times k1 and C as D plus n times k2. Then we just multiply A and C, so we get AC equals the quantity B plus n k1 times the quantity D plus n k2. And then you can expand this, and once you combine these terms here and factor it, you get BD plus n times the quantity BK2 plus DK1 plus NK1K2. And since you have an integer here times n plus BD equals AC, that tells us that AC is congruent to BD mod n. And we proved what we want to show. Let's look at one final proposition. If A is congruent to B mod n, and E is an integer that divides A and B, then A over E is congruent to B over E mod n over the greatest common divisor of n and E. So we'll start by doing exactly what we did before, which is by letting A equal B plus k1n. And we want to show that if we divide both sides of this equation by E, so we get A over E equals B over E plus k1 times n over E, then this part of the equation here is a multiple of our modulus up here. In essence, we want to show that n over the greatest common divisor of n and E divides k1 times n over E. So to do this, we first let n equal k2 times GCD of n and E, and E equal k3 times GCD of n and E, where k2 and k3 are some integers. Then this boils down to proving that k2 divides k1 times k2 times GCD of n and E over k3 times GCD of n and E. If we cancel some terms out on both sides, we see that this boils down to proving that k1 over k3 is an integer. In other words, does k3 divide k1? if we go back to the top, we see that we haven't actually used the condition that E divides both A and B. So we can say that E divides A minus B, and therefore with our expression over here, E divides K1 times N. So if we substitute what we let N and E be, this equation becomes K3 times the GCD of N and E divides K1 times K2 times GCD of N and E. And if we divide out the greatest common divisors on both sides, we simplify it to K3 divides K1 times K2. And now, since we're trying to show that K3 divides K1 only, this is equivalent to showing that the greatest common divisor of K2 and K3 is 1. Because then K3 would have to divide K1 entirely, and it wouldn't get any factors from K2 to help it. But this is pretty easy to show. Let's say, for the sake of contradiction, that the greatest common divisor of K2 and K3 were equal to A, where A is some integer greater than 1. Then we can write K2 equals A times L1, and K3 equals A times L2 for some integers L1 and L2. Now substituting back into the equation here, we see that N equals L1 times A times the greatest common divisor of N and E, and E equals L2 times A times greatest common divisor of N and E. Now if you look at these two numbers here, they both divide N and E since L1 and L2 are integers. But they're each bigger than the greatest common divisor of N and E, since we multiplied that by A, which is bigger than 1. Therefore, this must be the actual greatest common divisor of N and E. And since the greatest common divisor is the greatest common divisor, that's a contradiction. We can't have a divisor greater than the greatest common divisor. And therefore, we've actually proven our theorem. If we go back and we say that K3 divides K1, and go back through these steps here, then we'll have proven what we wanted to show. Now let's look at one more property, exponentiation. So if A is congruent to B mod n, then A to the E is congruent to B to the E mod n. Maybe pause the video and try to see if you can solve this yourself. So of course we want to first start writing A equals B plus K1n, where K1 is some integer. And then here we can plug in this B plus K1n into our expression for A. So we want to show that B plus K1n to the E is congruent to B to the E mod n. Now, one way to do this is with binomial theorem, and I encourage you to do that yourself if you would like to. But another way to do this is simply subtracting B to the E from both sides, or just moving it over to this side. And we want to show that B plus K1n to the E minus B to the E is congruent to 0 mod n, or in other words, n divides this expression on the left. So what we can do is factor this expression. We can factor it as B plus K1n minus B, which is this thing minus this thing here, times B plus K1n to the E minus 1 plus B plus K1n to the E minus 2 times B, plus the quantity B plus K1n times E to the 3 times B squared, and all this going on to B to the E minus 1. And if you want to convince yourself why this factoring works, you can pause the video and do that. Basically, you'll want to multiply each of the terms in this side of the expression with the terms in the sum over here, and kind of add them up, and you'll see things cancel out. So do that for yourself if you wish. And this side over here contains B plus K1n minus B, which is just K1n. So this product here contains a factor of n and then a bunch of integers. So obviously it's going to be congruent to 0 mod n. I hope I haven't bored you with theorems, so let's actually finish off by looking at one problem. This is from the 2014 AIME, number 8. The positive integers n and n squared both end in the same sequence of 4 digits a, b, c, d when written in base 10, where digit a is not 0. Find the 3-digit number ABC. So if you want to pause the video and try this out yourself, I encourage you to do so. Okay, let's start by converting this problem from words into numbers. So the first statement says They both end in the same sequence of 4 digits A, B, C, D when written in base 10. What this means is that n squared is congruent to n mod 10,000. If you're having trouble seeing this, let's just say that n squared equals some digits, and then A, B, C, D, and n equals some digits, and then A, B, C, D. Now, if we subtract n squared and n, we get a bunch of digits and 0, 0, 0, 0. So clearly 10,000 must divide this because anything followed by 4 zeros is a multiple of 10,000. So this tells us that n squared is congruent to n mod 10,000. The next step is subtracting n from both sides, so we get n squared minus n is congruent to 0 mod 10,000. Then we can factor the left side as n times n minus 1 is congruent to 0 mod 10,000. So we can write 10,000 as 2 to the 4th times 5 to the 4th, and these factors must appear in the product n times n minus 1 in some form. So we might have some 2's over here, and some 5's over here, and some 2's or something like that, and we end up with 4 of these in total, 4 2's and 4 5's in the factors. The first thing I want to claim is that it's not possible to have both a 5 and a 2 be factors of either one of these. And what we'll see is that if 5 and 2 are both a factor of n minus 1, for example, then n minus 1 would have to end in 0, since it's a multiple of 10. And n would end in 1. So n can't have any factors of 2 or 5, because it ends in 1. Therefore, n minus 1 actually has to have all the factors of all 4 factors of 2 and all 4 factors of 5. So 10 to the 4th has to divide n minus 1. And the problem with this is that it means that n is congruent to 1 mod 10,000, which says that n is 0, it ends in 0, 0, 0, 1, which is clearly not what we want, since the problem statement says, I can scroll up here, it says that digit A is not 0, and this is a contradiction. If we go the other way and we assume that there was a 2 and 5 in n, then we would see that n ends in 0 and n minus 1 ends in 9, which means that all the factors of 2 and 5 would have to be in n, so 2 to the 4th times 5 to the 4th divides n, which means that n ends in 0, 0, 0, 0, since it would be congruent to 0 mod 10,000. This also doesn't work. So clearly, one of these, n and n minus 1, one of them has all the factors of 2, and the other one has all the factors of 5. Let's start by assuming 5 to the 4th divides n, and 2 to the 4th divides n minus 1, for example. Then we end up with the set of congruences, n is congruent to 0 mod 625, and n is congruent to 1 mod 16. So we can write n equals 625 times k, and then we get 625k is congruent to 1 mod 16. Since 625 equals 16 times 39 plus 1, 625 is congruent to 1 mod 16, and this reduces to 1 times k is congruent to 1 mod 16, which means that k is congruent to 1 mod 16. So let's go a step further. Let's just say that k equals 1 plus 16k1. Then we can write n equals 625 times 1 plus 16k1, and we'll be left with 625 plus 10,000 k1. So this tells us that the last 4 digits of n would be 0625, since we have to add 10,000 to it. And this doesn't satisfy our condition, since the digit a would be 0. So we have to look at the other situation. So going this way, 5 to the 4th divides n minus 1, and 2 to the 4th divides n instead. Then we write n is congruent to 1 mod 625 and n is congruent to 0 mod 16. This is our set of congruences. So we can write n equals 625k plus 1. Then we write 625k plus 1 is congruent to 0 mod 16. We used earlier the fact that 625 is congruent to 1 mod 16. So we'll plug that in here. So this becomes 1. 1 times k plus 1 is congruent to 0 mod 16. That tells us that k is congruent to 15 mod 16. So then we plug this back into our equation for n up here, and we get n equals 625 times 15 plus 16k mon. And we expand this out and we get 625 times 15 plus 10,000 k1. So now 625 times 15 equals 9375. And n must end in these 4 digits, since n is congruent to this mod 10,000. So adding 10,000 or any multiple of that to this number will keep these 4 digits the same. Now if we go back to what the problem, was asking for, we see that it wants the 3-digit number ABC. And the number we got at the end was that it ends in 9375. And the ABC, these 3 digits over there, are 9, 3, and 7. So if you were taking the AIME, you'd write down here 937 and you'd be done. Alright, I hope you enjoyed that video on modular arithmetic. I know it was a lot of theorems that we were just proving, but glad you stuck around. I'll see you in the next video. Bye.